Welcome. In the previous video, you learned what integration by parts is. To apply this technique, you need to make several choices. Indeed, calculating primitive functions is something of an art, and there are no fixed rules you can follow that will always lead to success. In this video, I will share with you some ideas that can help you when applying integration by parts. Observe that integration by parts turns the problem of solving one integral into the problem of solving another integral. The goal should thus always be to try to make the new integral easier than the old one. If you look back to the example we did in the previous video, the integral of x times e to the power 4x was transformed to the easier integral of e to the power 4x. Okay, suppose you have decided to try to use integration by parts. You have split up the function you need to integrate as f of x times g of x. Which of the two functions should we differentiate and which should we integrate? In the example of x times e to the power 4x, we considered what would happen for both functions if we integrate and differentiate them. And this is what you should do in general, basing your choice on which resulting integral will be simplest. If you really have no idea, you can always try both options and see whichever works best. However, consider the following table. If you read it from left to right, it tells you what the primitive function is. If you read it from right to left, it tells you the derivative. Notice that the functions in the top row are essentially just as difficult on the left and right hand side. The exponential function stays the same if you integrate or differentiate it. The sign just turns into a cosine upon either integrating or differentiating. Thus, if one of your functions is the exponential function, for the new integral it does not matter whether you integrate or differentiate this exponential function. For the polynomial functions in the second row, you see that integrating increases the degree of the polynomial by 1, while differentiating decreases the degree by 1. Thus polynomials become moderately more difficult when integrating and slightly simpler when differentiating. Finally, the function natural logarithm of x in the bottom row becomes extremely much simpler when differentiating, while the primitive function of 1 over x is quite complicated. You see that the lower the function you consider occurs in the right column, the more you would like to differentiate it, whereas the higher the function occurs on the left, the less you'd mind integrating it. Thus typically, it is best to integrate exponential functions, while if one of the functions in your product is the natural logarithm, you really want to differentiate that one. For example, for the integral of x times sine of x, you want to differentiate the function x from the second row, making it a little easier, and integrate the sine of x, which is above it in the top row. So integrating or differentiating really does not matter for the sign. For the integral of x times the natural logarithm of x, you want to integrate the x from the second row, because the logarithm of x is now below it in the third row and thus becomes much easier upon differentiating. Indeed, you want to differentiate the natural logarithm of x so badly that you want to use integration by parts even for the integral of just logarithm of x, where you cannot see a product at first. How can you rewrite the natural logarithm of x so that it is a product? Well, if ln of x is one of the two functions, the other function must be the constant function 1. Now, applying integration by parts on 1 times ln of x, where we of course differentiate the logarithm and thus take the primitive of 1, we obtain x times ln of x minus the integral of x times 1 over x. The new integral is the integral of the constant 1, which is easy. We find that the integral of ln of x equals x times ln of x minus x plus a constant. Finally, I want to show you an advanced trick that you can sometimes use. Consider the integral of e to the power x times cosine of x. It is a nice product, so you want to use integration by parts. Because both e to the x and cosine of x are in the top row of the table, it does not matter which one we integrate. But my personal preference is to integrate e to the power x. Then we obtain that the integral of e to the power x times cosine of x equals e to the x times cosine of x plus the integral of e to the x times sine of x. Notice that you get a plus sign because it's a minus minus. 1 minus from the integration by parts and 1 minus from the derivative of the cosine equals minus sign. The new integral e to the power x times sine of x looks just as hard as the original one, so it seems we have not achieved much. But it's a product, so we can use integration by parts again. Let's integrate e to the power x again and differentiate sine of x. This gives that the integral of e to the power x times cosine of x equals e to the power x times cosine of x plus e to the x times sine of x minus the integral of e to the power x times cosine of x. There does not appear a minus sign differentiating the sine function, so we keep the minus of the integration by parts this time. We seem to be back at square one. We have the same integral as before. However, now we can use an amazing trick. Notice that on the left we have plus 1 integral of e to the x cosine of x, whereas on the right we have minus 1 integral of e to the x cosine of x. Moving this integral from the right hand side of the equation to the left gives 2 times the integral of e to the x cosine of x equals e to the x cosine of x plus e to the x sine of x. Dividing by 2, we find our answer, the integral of e to the x of cosine of x is 1/2 e to the x times cosine of x plus sine of x. Somewhere along the way we lost our constant of integration, plus c. If you look carefully, it's exactly when we apply the trick to shift the minus integral of e to the x cosine of x to the left hand side. Losing the constant of integration happens whenever you apply this method, and in this case it is easiest to just add the plus c at the end. Now, try solving some integrals yourselves.